In today's video, we'll cover part 1 of Module 1, Kinematics of a Particle. The objectives are to introduce the concepts of position, displacement, velocity, and acceleration, to study particle motion along a straight line and represent this motion graphically, to investigate particle motion along a curved path using different coordinate systems. Before we start going through our module, I wanted to do a quick overview of mechanics. So mechanics is the study of how bodies react to a force acting on them. Mechanics is divided in two areas: statics, which is the study of the bodies in equilibrium. This is when the summation of our forces are equal to 0. And then we have dynamics. In dynamics, our particle is in motion. We can divide this in two areas: in the kinematics, which is concerned with the geometric aspects of the motion, so the location, the velocity, the acceleration, and then kinetics, which is concerned with the forces causing that motion. In this module, we're going to start with the kinematics, so position, velocity, and acceleration, and we're going to study it in different coordinate systems. We're going to start talking about a rectilinear motion, then we're going to talk about the curvilinear motion. The curvilinear motion, we're going to divide it in three main coordinate systems: regular rectangular components, so our x and y coordinate system. Then we're going to talk about two other coordinate systems, which is the normal and tangential coordinate system, and then the cylindrical components. In part 1, we are going to cover section 1 and section 2, so rectilinear kinematics. Starting with section number 1, the continuous motion. I have this video here just to have an idea of what we're going to discuss. So as we can see right now, the car is just going in a straight line, but the car is accelerating, decelerating, the velocity is increasing, the velocity is decreasing. So after watching this video, we can ask some questions that I want you guys to think about a little bit. So when was the velocity positive? When was the acceleration negative? Was the car moving backward when the acceleration was negative? Not necessarily, right? So to start with the rectilinear kinematics, then we have a particle that travels along a straight line defined by the coordinate axis S. So we have the origin, we have our particle, in this case the car moving, and then we can define the position of that particle respect to the origin with a vector S. So position we're going to define with a vector S, and then the displacement of that particle is defined at its change in position. So if this was the original position of the particle, we called S. This is the final position, we called S prime. Then the displacement, so how much that particle displaced from its original position to its final position, that we're gonna call delta S. So delta S, or displacement, is the final position of the particle minus the initial position of the particle. So the total distance traveled by the particle is a positive scalar that represents the total length of the path over which the particle travels. So this is our first kinematic that we are going to study, which is position. Then we're going to talk about velocity. Velocity is a measure of the rate of change in the position of the particle. Rate of change in the position of a particle. It's a vector quantity, so it has both magnitude and direction, and the magnitude of that velocity is called the speed. We have units of meters per second if we're talking about the international system, or units of feet per second if we're talking about the imperial system. The average velocity of a particle during a time interval then is going to be that displacement, or that change in position, over the change in time, or the total time, the time that it took to go from position 1 to position 2. So in this case, we have our origin, we have our particle in its initial position, our particle in the final position, we have a change in positions or displacement that happen over a time interval. Therefore, it's moving from position 1, position 2 to the right. The velocity is in that direction, and this will be our vector, our velocity vector. We can talk about also instantaneous velocity, which is the derivative of that position over the time change, right? So at each position, so if we take a very small interval, we can find the velocity at different time intervals, right? So we have an average velocity, so the velocity that it took to go from point 1 to point 2, the velocity in between that interval, or we can talk about instantaneous velocities, that in that case we just get a very small interval and we can find it by derivating the position vector over the time. The speed is the magnitude of the velocity, and we can also talk about average speed, which is the total distance traveled divided by the elapsed time. This is different with the average. With the speed, for example, here we have position on origin. We have our initial position, which is P here, final position P prime, but our particle moved first to the right and then it went backwards or moved to the left to the final position. So the displacement, if we keep following our definitions, will be the final position minus the initial position. So this is the displacement of that particle, but the particle moved all this, right? So this is the total distance traveled. So this was not the total distance, this is the total distance traveled. So we can talk about an average speed, right, which will be that total displacement over that time interval. So these are two different, the velocity, the average velocity and the average speed. Finally, we can talk about the acceleration, which is the rate of change in the velocity of a particle. It is a vector quantity. The typical units are meters per second square if we're talking about the international system, or feet per second square if we're talking about the imperial system. Then same idea, we have our particle with an initial velocity v, and then our particle with a final velocity v prime, and then that change in velocity will be our acceleration. So the average acceleration during a time interval, delta t, will be the change in velocity over that time interval. We can also find the acceleration at specific times. So the instantaneous acceleration, which is just now the derivative of that velocity vector over the time. The acceleration can be positive if the speed is increasing, or negative if the speed is decreasing. So to remember this, I like the car example, right? The car is never moving backwards, it's always moving forwards, but that acceleration is changing, right? If that speed is increasing, so if the car is going faster, then we have a positive acceleration. If the car is going a little slower, then we have a negative acceleration. So if we find, we have now two relationships. We have a relationship between the displacement and the time, which is the velocity, and we have a relationship between the velocity and the time, which is the acceleration. If we play with these two equations, we can also find that the acceleration times the change in displacement is equal to the velocity times the change in velocity. So a summary of the kinematic relationships in the rectilinear motion, if we differentiate the position to get velocity and acceleration, so if we can find the velocity if we differentiate that vector position. We can find the acceleration if we differentiate the velocity over the time, or we can use this third relationship. If you guys notice, the velocity and the acceleration here depends on the time. If I don't have the time, I have this third relationship, which depends on the velocity and the displacement. So these three relationships here are going to be the basics of the first two modules of our class. So if we integrate the acceleration for velocity and position, if we integrate, then we can find here, if we integrate the velocity between the initial velocity and the final velocity, Then we integrate this one on the other side between the initial time and the time that it took to go from point A to point B. And we can also integrate the position here to find, or integrate the velocity to find the position. Note that SO and VO represent the initial position and the velocity of the particle at the time interval 0. So again, we have these three relationships. We can derivate to go from, let me see if I can, so we have S, B, A. If we have the position, we can derivate this position to find velocity. We can derivate the velocity to find acceleration. If we're gonna go back, we can integrate. So if we have the acceleration and I want the velocity, I can integrate in terms of the time to find velocity, and then if I have velocity, I can integrate in terms of the time here to find my position vector. So this is the whole idea of how we're gonna work on these few modules. If we integrate these three relationships here, so the three kinematic equations can be integrated for the special case when acceleration is constant. So if you guys notice here, we have acceleration. So if the acceleration is constant, to obtain very useful equations. So here we have the example of how to integrate these three equations. I will create an additional video for you guys to see the step-by-step of how I can integrate this to get these relationships here. But an example of constant acceleration is the gravity. Example, the body freely falling towards Earth. In this case, these three relationships that we have here turn into these three relationships only for constant acceleration. So if the acceleration changes with time, then I do have to integrate or derivate. If my acceleration is constant, then I can go ahead and just use these three relationships. This is example number 1. Please go to the videos on Canvas. For example 1, I'll solve it step by step using my iPad, so it's easier to go through the steps. The next thing that we're going to cover is the rectilinear kinematics, erratic motion. For this, I have this video here. I like this video because it gives us like a visual. So after watching this video, we can ask some questions. So is the biker's path simple enough to describe using just one single equation, or question in this case? When the motion becomes too complicated geometrically, what other method can we use to analyze the motion, right? So the biker is going almost in a straight line, right? But it's going up and down, it's accelerating, decelerating a lot. So when we have complicated paths like this, then there's easier ways to see that path, and that's by graphing. So graphing provides a good way to handle complex motions that will be difficult to describe with formulas. Graphs also provide a visual description of motion and reinforce the calculus concepts of differentiation and integration as used in dynamics. The approach builds on the fact that slope and differentiation are linked, and the integration can be thought as finding the area under the curve. So we already talked about if I have the displacement and I want to find the velocity, I can differentiate. If I have the velocity and I want to find acceleration, I can differentiate. If we think about the definition of differentiation, we know that is the slope of that graph, and if I want to find, then integrate. If I want to go backwards, then I can just find the area under the curve to find those relationships. So for example, if we have the displacement graph, right? So we have the displacement or position vector graph against the time, and based on this origin, so I have different time intervals. If I want to find the velocity, so we know from our relationship that if I have position, I want to find velocity, then I have to differentiate. But I also know that the definition of differentiation is the slope of that line, right? So if I have a little interval here and I find the slope, so the initial velocity will be that differentiation between ds and dt at the time equal to 0. If I find this, then I'll have my first point on the graph. Then if I grab another point and I find the slope of a line crossing that point here, then I'll have my velocity at 1. And then if I keep doing that infinite times, then you have an idea of that VT relationship. If I now have the VT graph, we also know that if I want to find the acceleration, now I just have to differentiate that velocity function. So now that will be again the definition of differentiation, which is the slope under the curve. So if I start drawing lines in that graph, then and differentiating the time interval, then I can find all the points in my AT graph. Then if I want to go backwards, right? So we know now if I have the acceleration, I want to find the velocity. We saw that we need to integrate. We know that the definition of integration is just the area under the curve. So if you grab interval here, for example, between 0 and t1, and you find the area under the curve between 0 and t1 again, then you will find that change in velocity, right? So you'll find that change in velocity, and if you keep doing that a lot of times, then you can keep finding those change in velocity between the time intervals and find a graph for the velocity. And then you can do exactly the same. Oh, I have it here. Exactly the same now if you have the velocity and then you want to find the displacement table, the displacement graph. Remember that we also have a relationship that does not include the time, right? So this one is the AS graph. This one has a additional step in order to draw that VS graph, but we can just play with this equation. So if we solve here, if we integrate this, so we have between S1 and S2, and then this side of the equation we integrate between V1 and V2, we have that 1/2 V1 squared minus VO squared is equal to this side of my graph, right? And this side of the equation, is just the integration between S1 and S2 in the A graph, right? So if I find that area under the curve between between initial position and final position S1, then you'll have this side of the equation. And then you can just solve for B1 here, right? So you can move this to the other side, square root, or move this to the other side and find the square root of B1. So you just solve for B1 and that will give you the first point. So you just have to do that extra step to solve for B1, but you can definitely make a VS graph if you have your AS1. I already talked a little bit about, now if we want to go backwards, right? So now we have AS to VS, but we can also go from VS to AS graphs. So same, we know that the acceleration now is V dV ds. So now this is just the slope here. So if I find the slope in the VS graph here and multiply by the velocity at that interval, then you'll have your acceleration. So we can obtain the AS plot from the VS curve as well. Again, for example number 2, I'll solve it in my iPad to go step by step. So please refer to example 2 in the Canvas module 1. That's everything that I have for this video. We'll keep going with the general curvilinear motion next week. Thank you.